Hello and welcome, and thank you for joining us today. My name is Alex. I'll be your moderator for the day. We're very excited to host this joint webinar with our long-term material partner, BASF 4AM. In this webinar, we'll be exploring the synergy between our advanced additive technology and their high-performance material. Presenting today, we have Ray Jones from Farsoon Technology. Ray? Ray is an industry veteran with over a decade of experience in the field, 6 of which are with Farsoon as a polymer application specialist to ensure customer success, focusing on polymer applications and material and machine development and integration. Also presenting today, we have Dr. Shir Mohammadi, as his friends call him, Mason, from BASF 4AM. Dr. Shir Mohammadi has a PhD in material science with a focus on micro-macro structure properties relation, and has a decade of experience in material and process development for various 3D printing technology. Currently, he is business development manager at BASF, where he focuses on customer-centric solutions for all 3D printing technologies, including powder, filament, resin, and simulation software. And finally, we have Johnny Drew with us today as well. He's the Polymer Product Director from Farsoon Technology. He's been with Farsoon for over 7 years and has a wealth of knowledge in polymer. If you have any questions during the webinar, feel free to drop them in the Q&A session, and we'll be answering them at the end of the presentation. Now, with all that out of the way, please sit back and enjoy the presentation. Ray, please take it away. I'll give you control. And we are ready to go.
Awesome. Thank you, Alex. So before we get started, I just want to thank everybody for joining our webinar this morning, taking time out of your morning to learn a little bit about polymer potentials with TPU and Farsoon's machine platforms. And I'm having trouble with the slide control. Okay. So before we get started, I just wanted to take a look at the agenda real quick, what we're going to be talking about today. So the first part, of course, was our introduction to myself and Misam. Then we're going to jump into BASF, 4AM, and Farsoon's partnership. Then we're going to follow that by looking at Farsoon at a glance, just what we offer as far as our flight technology is concerned. And then we're going to take a look at the actual flight fiber laser technology itself, what it offers, right? So it'll offer speed, productivity, and then we'll highlight on our open platform strategies and what that means for the industry. And then we're going to finish up the webinar focusing on BASF 4AM's material portfolio with plastic laser powder bed fusion systems, primarily PA11 and TPU, their features and applications. And then we'll take a look at 4AM's new innovative lattice engine software with high design. And then we'll take a look at some customer production cases. So moving into what Farsoon offers, right? So Farsoon offers a complete manufacturing solution. So Machine Solutions, Farsoon is a truly open platform with a wide portfolio of systems ranging from small rapid prototyping and material development platforms, medium-sized serial production runs, and then large oversized part bed capabilities. What we also offer is material solutions. So Farsoon manufactures our own PA12 and PA6 unfilled and reinforced materials, but we do partner with third-party material manufacturers like BASF 4AM to help fill our portfolio offerings. We also offer software solutions. So we developed our own open build preparation and machine operation software. This includes a degree of real-time monitoring software, open parameters that allow you to change certain parameters that allow you to kind of get into material production, get the material properties that you want out of the material that you're processing in our machines. And then we also offer applications. Farsoon offers a customer-centric applications, team-based out of each office with benchmark production, machine material processing, testing, and qualification capabilities. And then our fully open system, right? So Farsoon platforms are truly open for material parameters and collaborations. Farsoon lets our end users navigate the open market for material use, as long as it fits within the desired system's operating conditions. Options that open up both build and part parameters, heating control, layer thickness, scan spacing, fill and outline, laser power, to name a few, and is open to third-party material collaborations. So Farsoon is a global AM technology. Farsoon Worldwide has over 25 years of experience in powder bed fusion and the additive manufacturing industry. Farsoon is headquartered in Changsha, China, and has fully operational offices here in the US, in Austin, Texas, and then in Stuttgart, Germany. Farsoon also has partnerships with resellers, expanding 30 countries globally. And as of November of 2023, we've sold over 1,000 units globally. So taking a look at Farsoon and BASF Ford AM's partnership. Farsoon and BASF Ford AM's partnership started in 2015 as they established an initial collaboration with Ford AM's ultrascent material on Farsoon's high temp 251P system, pictured on the left-hand side. Over the course of the next 4 years, between 2015 and 2018, BASF Ford AM launched their ultrascent material for use on laser powder bed fusion systems. In 2021, BASF Ford AM China installed Farsoon's HT403 at their AMTC Shanghai facility, which is pictured right here. And then in 2023, BASF Ford AM North America installed Farsoon's Flight 403 P system at their AMTC Detroit facility, which is pictured right here with the esteemed Jeremy Voss, if you had the pleasure of meeting him. And then in the same year, Farsoon also partnered with BASF Ford AM to introduce their UltraSim 3D Lattice engine, which both parties showcased at last year's Formnext event. So taking a look at the flight machine portfolio that Farsoon offers, we have 3 flight platforms with various options for each system. Our first platform, the Flight 252, comes in our HT or ST models. HT has a max processing temperature of 220 C and a 250 by 250 by 320 millimeter build envelope and a 300-watt fiber laser. Our ST model has the same specs as the HT, but with an increased processing temperature of 280 degrees C. This platform is great for material development, high temp applications, rapid prototyping, small batch production. Next, we have our Flight 403P platform made up of the SS and the HT 403. Both have a build envelope of 400 by 400 by 450 millimeters, but there's an option to increase the Z height to 540 millimeters on both the SS and HT. The SS option has a max processing temperature of 190 C, while the HT has a max temp of 220 C. Both models come with either a single 500-watt laser or a dual 300-watt laser configuration. This platform is great for ultra-fast production, fine detail, and functional parts. And then lastly, we have our Flight 1001P platform with a build envelope of 1000 by 500 by 450 millimeters and a max processing temperature of 220 C and either a dual or quad 300-watt laser configuration. This platform is great for oversized parts that can't fit in traditional SLS build envelopes, low cost per part production, and hands-off continuous operation. So taking a look at flight fiber laser technology compared to kind of standard CO2 laser platforms that you would see on the market today. So we can see a couple key differences. The first key difference is laser beam spot size. Traditionally in a CO2 SLS system, they use a laser with a spot size between 400 and 500 microns. This usually restricts our minimum feature size to about 1 millimeter, or about twice the size of the laser spot size. We can see though, with a fiber laser, we can get down to around 100 microns and the contour or outline pass to get real fine feature details, around 0.3 millimeters. But we're also able to open up the fill pass to 1,000 microns to decrease build times and increase scan times. The second key difference is laser power. The standard operating range for a CO2 laser is around 30 to 100 and watt, 30 to 120 watts. Fiber lasers, which are traditionally used in metal laser powder bed fusion systems, because of their more dynamic power range, can access wattages between 300 and 500 watts. This gives us not only overhead on material processing ability, as some materials may need more laser energy than others, but this also unlocks a significant increase in scan speed, traditionally from 10 meters a second on the low end to about 20 meters a second on our flight systems. And the last key difference between the CO2 and fiber lasers is their average lifespan and operational stability. So on average, a CO2 laser has a lifespan of approximately 40,000 hours. This kind of averages out to about 3 to 5 years of operational use, depending on power usage. So the higher you fire a laser continuously, the less overall life it's going to have in the system. Uh, the power stability of the laser, how much it drifts during operation, can reach upwards of plus or minus 5% during extended continuous use. But on the other hand, a fiber laser, because of its unique construction, has an average lifespan of about 100,000 hours, or about 10 years. This significantly increases the value of the machine, reduces maintenance and replacement costs of multiple CO2 lasers over the same time period. So kind of want to showcase the difference between a CO2 laser and a flight laser system. So on the left-hand side, uh, we can see uh, BASF Ford AM TPU's material being scanned by both the CO2 and the flight system. The first thing you'll notice is how much smoke there is during the sintering process using the CO2 laser compared to the clean sintering process of the fiber laser. This is due to the way the material absorbs the energy of the laser and leads to increased laser life and reduced machine turnaround time after each build. The second thing you'll notice is the difference in sintering speed between the two. Hello?
Ray, are you there?
Hello? Hello? Hello?
Yes, Ray.
Can you hear me?
Yes.
Okay. Sorry about that, everyone. uh, Apologize. So
Mhm.
the second thing we can notice is the scan speed between the CO2 and the flight system. This is the same cross section between each build. The flight system scans a layer in 23 seconds, while the CO2 system scans just right over a minute. So taking a look at our multi-laser flight technology, we can see first on the 403 dual laser platform, each laser has full coverage of the XY build area. You can even assign each laser to specific parts during the sintering process. Second, the quad laser 1001 platform, where lasers 1 and 2 control the left side of the build XY build area, and lasers 3 and 4 control the right side of the build area. This is, however, an overlapping area in the middle of the build area, where stitching occurs. This lets us either build platform or let us build small or medium-sized parts in the build platform with a stitch area in the middle for large parts that can span across the entirety of the build area. These multi-laser configurations enhance productivity and throughput without sacrificing part quality. So taking a look at our flight HT403 productivity. The 403 platform is designed for efficient turnover in a manufacturing type environment with exchangeable feed and build cartridges, which are 1 and 2, that can be staged and hot swapped at the end of each build. External build cooldown options pictured in 3 and 4, and then a closed loop breakout sieve and material mixing station, which we call our powder management system, pictured as number 5. Looking at a production type scenario with a dual laser Flight 403, an end user can expect to complete 2 builds in a 24-hour period. So what does that all mean? So looking at productivity, we put into perspective the level of productivity that our flight system offers over traditional SLS technologies. We put together a full pack-out build of the same standard size parts and a standard SLS system that you may find out on the market, compared to our CO2 403 system, our single laser and dual laser Flight 403 systems, and then our quad laser 1001 flight system. So a standard CO2 laser SLS system with a full pack out of 266 parts will complete a build in about 42 hours, almost 2 days for a build, which is not ideal in a manufacturing type environment. So looking at our HT403, which is comparable to most mid-size SLS systems currently on the market, we can find that although, yes, we are able to nest 266 parts in the build envelope, we are also looking at a 25-hour build, which is better than 42 hours, but still not quite ideal in a manufacturing type environment. So that's where our single laser flight system comes into play, cutting build time down to a little over 16 hours, giving us 2.5 times the productivity yield over a standard SLS system. Moving to our dual laser flight system, we can see that we can cut down the build time even further to a mere 10 hours, giving us almost 4.5 times the productivity yield. It's 266 parts in 10 hours compared to 42 hours in a standard SLS system. And then finally, to round out our system comparison, I want to take a look at our quad laser 1001P. As we can see, we're able to complete a 13-hour build and produce 784 parts. It's 3 times as many parts in our mid-sized platforms completed in less than a day. So along with our open parameter, we also offer open material strategy, right? So we're not material locked like a lot of our or other SLS powder bed fusion systems on the market today. Meaning end users have full freedom to explore solutions of their material needs. Each platform includes full control to edit part and build parameters, and includes full access to a list of standard material configuration files from Farsoon, as well as our partners ready for series production. Farsoon has partnered with BASF 4AM to qualify polypropylene, neat ESD, and carbon-filled PA11 materials, and then TPU 88A in our flight platforms. And I will hand it off to Misam.
Thank you, Ray. Hi, everyone. Thank you for coming. Good morning, good afternoon. So if I start about the powder one, I want to give a brief introduction about BASF Forward AM. We are a 3D printing solution company that we offer as an independent material provider. We offer over 800 different solutions for 3D printing. We provide materials and software for different 3D printing technology, photopolymer, filament, polymer powder, and metal filaments. We have over 250 employees in our group, headquartered in Heidelberg, Germany, and in North America and Asia. We have application development and sales body of Forward AM, which is headquartered in Heidelberg, as I mentioned. But majority of our development, material development, is in Europe and Ray mentioned we have 2 application centers, one in Detroit, one in Shanghai, that we have different machines, including a Fortune system for powder base. Again, our offering is in 4 categories. The top one is mentioning our 3D printing service and solution. We offer simulation, design for additive manufacturing, lattice design, TCO, and life cycle analysis. We have different filament in our portfolio. Again, we offer material both as white label and BASF brand. The same is with our photopolymers. And the last one, which is our today's focus, is our ultra thin powder, which we have different materials for 3D printing in SLS or powder bed fusion technology. So we have 3 main category of powder-based materials: our nylon 11 products, our TPU product line, and polypropylene. For the sake of time today, we'll mainly focus on nylon 11 and TPU lines, but if someone has any question about polypropylene, we'll discuss about, and I'll be happy to answer questions. So we get into ultra thin PA11 or nylon 11. So PA11 is a bio-based material. It's a derivative of castor oil, and it is used, or it is popular for being the most rugged or the highest toughness of materials in powder-based portfolio, powder-based technologies. In our portfolio, BASF has the material in a neat version, both black and natural color. Then we offer nylon 11 ESD, and we have a carbon fiber field and recycled carbon fiber field, which reduces the carbon footprint of the material to the lowest for field materials. Nylon 11, as I mentioned, it is a bio-based material. It is biocompatible, and it is highly ductile and rugged, so it has the highest toughness and elongation, as I mentioned, of powder-based technology materials. And the natural version of ultra thin nylon 11 meets USP class 6 and food contact for containers and applications like that. It provides the food contact requirement. It meets the requirements. And these are kind of the applications for nylon 11, both natural and white, black color. The reinforced one, nylon 11, as I mentioned, we have a carbon fiber filled version of it that offers both high impact resistance from nylon 11 and high strength and high rigidity and high HDT from being carbon fiber filled. So our P11 carbon fiber field, you can have the both, again, high impact of nylon 11 and high strength of carbon fiber field. We'll get into examples of both of these later during this presentation. So kind of giving you the difference between nylon 11 and nylon 12, which is highly comparable in terms of at least the modulus or the look of these two material. Nylon 11 is considered a material for functional prototyping or final part, and this one shows that the example of a drop test on a P12 part and a P11, and you can see P11 can handle, as I mentioned, rugged, high impact environment. Another example of that is snap feeds and parts that require a living hinge, is where nylon 11 is the only choice compared to other materials. And as I mentioned, the look and then the printability, the recycling is almost the same. And this one, for most of the designers, mechanical designers, stress strain curve is something that they are very familiar with for the yield and break. And kind of here compares the elongation and stress strain curve of these two materials. As you can see, again, nylon 11 has a significantly higher elongation at break in different orientation compared to nylon 12. This is another example of comparing the life cycle analysis of nylon 11 versus nylon 12 and an injection molded P6 or 66, which is the engineering nylons that are widely used in traditional manufacturing. And as you can see, the bio-based nylon 11 has significantly lower carbon footprint compared to incumbent and materials that are used in different platforms or is used with different materials in 3D printing. Again, I want to just give brief examples of, as I mentioned, the nylon 11 and its derivative. Here is an example. On the left side, we see the for orthotics and the braces for orthotics and prosthetic. It provides a lightweight and comfortable, breathable part, and it is fully customizable for different patients. This specific part was printed on a Farsoon flight system for productivity, as Ray mentioned, very fast printing parts. And it was nylon 11 black was used because I think, as Ray mentioned, they have a different wavelength. And for flight system, you require an absorbent, which majority of them go into the dark gray or black, and nylon 11 black on field one, then the neat nylon 11 black is a preferred choice for this specific application. On the left side, we show a bi-camera mount, which was a development by the customer for Canyon. They had two main purposes. One is design for additive that here I'm showing, like, it was they used the UltraSim 3D simulation software to design to reduce the vibration. Most of these parts would unscrew over the time of riding the bike, and that would cause the falling of the camera. And the first part of that project was designing a part that would withstand the vibration for the camera mount for off-road bike, and the second part, choosing the material that can withstand the both strength and the high rugged environment, high strength, which again the preferred choice was nylon 11. This is the example. Over 18,000 parts has been sold of this part, and if someone is interested, they can use this website to purchase the part. Again, it was both for they use the simulation to design specifically a part that eliminates the vibration and again withstands those rugged environment. And it's made with PA11 CF from BASF forward AM with Farsoon system. The other example is a PA11 black. As I mentioned, majority of these parts are for rugged environment. In this particular application, they needed a part replacement for repair, and it needed to withstand again rugged environment, vibration of ball. So for replacement, they used the solution was a nylon 11 that again it was economically more viable compared to the traditional manufacturing because there was no mold available, and again it meets the requirement of both economy and sustainability for this specific part. And I want to emphasize enough because of the rugged environment, high vibration, high impact during the lifetime of these parts, nylon 11 was the preferred choice for this application. These are a few examples that was provided by Solaxis, a service bureau in Canada that uses BASF nylon 11, BASF forward UltraSim, different products that we have with two Farsoon machine, both flight and CO2 laser. You can see on the top left, it shows those snap feed parts that you require, very thin walls that withstand bending and snapping and impact. On the top right is a protective case for locomotive. As I mentioned, every time you're trying to have a rugged part that withstand impact, nylon 11 is a preferred choice. And on the bottom left, you can see the material is possible to smooth and have injection molding surface quality for final production or bridge production type application. And the one on the left, again, is a safety cover to handle impact. So anywhere in a short summary, anywhere we require high impact and the parts require to be in a rugged environment, low temperature, nylon 11 is a preferred choice compared to other plastics in SLS technology. Now we get to TPU materials. For SLS technology, Forward AM offers three main materials. All of them actually are printable on Forsoon machine, either flight system or CO2. TPU88A is a natural color TPU. TPU88 black version of that. And the latest one that we offer is a semi-rigid TPU98 LT. So I'll get into detail of these material each later, but I want to kind of a little bit explain why these materials are preferred choice of elastomers compared to others in the market. Again, ultra-thin TPU, we are the only one that offers the full solution for the materials. The TPU that we offer in our portfolio is considered a mid-hard TPU, around 85 to 90 TPU, but with ultra-thin 3D simulation that we offer, the lattice design, you have the flexibility of changing the duramer of the material for different application. And these are the examples of parts printed with TPU for, again, healthcare, orthotic, and prosthetic, for automotive parts, both inside, interior and exterior of the part. I'll get into the example. For protective gear, again, helmet from Zenith was #1 safest NFL helmet for 2024. Again, use BASF ultra sim simulation to design the helmet, as well as BASF TPU88 to print the parts, the interior of those parts. And what makes us unique is, as I mentioned, we offer a material, a full solution, including a flexible coating for 3D printed parts. Dyeing does not work for flexible material because when you stretch it, usually you see the crack in the dye for flexible part. But we offer a two-part urethane-based coating that works well with our TPU and for end-use parts or functional prototyping. I think briefly Ray mentioned the hyperganic, and I kind of mentioned in our ultra-thin 3D lattice design, we offer lattice design in our software, and we partner with Hyperganic to have our lattice library available on their website as a cloud-based system to design. Basically, you can design your parts and choose the duramer that you want. And with Hyperganic, you can put the skin, as I kind of mentioned here. This QR is available. They offer right now a 90 days free trial if someone is interested. You guys can email and we can provide you. But basically, the idea behind UltraSim is you can design your parts based on your need, your application need, and run the simulation. And once your parts are good, then you do the printing. And as I mentioned, the UltraSim is also available with the Forsoon machine. We have done the testing on the Forsoon printed parts, so it's available in our lattice library. Another thing that makes us unique is the certificate and testing that we have available on our TPUs. Here are examples of what we have done. So if someone is interested in more detail, I'll be happy to provide them, or I have the QR code of our site here, so you can see all of these tests and certificates are available for for our TPU, which helps for the functional part and as well as end-use production parts. I'll get into examples later how these will help for the final parts because it's qualified for those end-use applications for the performance cars, and it does not delay their shipment of those cars to dealership. Again, this is an example of bridge manufacturing or customizing your design without delaying or without sacrificing your quality. This is the last example of TPU 88A Black. I want to hand it to Ray. I think he was working with the customer on this specific one, so I want him to mention in detail the application.
Yes, thank you, Misam. So the first TPU customer application that I want to take a look at is from Sophos Robotics, located in Minnesota. Sophos had a need to protect the pictured teach pendants from normal wear and tear and abuse that this device may experience, just in everyday use. But because it was an older unit, replacement parts were difficult to find. And when they were found, they were rather expensive. So Sophos was able to design and print these protective cases using BASF 4AM's black TPU material and our Flight 403 system. Sophos, using our open parameter platform, was able to adjust the case's wall thickness and certain other properties to achieve their desired durometer for the effective protection. Their customers have reported satisfaction with the surface finish of the parts and were impressed with the overall quality of the parts themselves, which I think speaks a lot towards 4AM's material and our ability to process that material on our machines. The second TPU customer application that I want to highlight is the 4-point insoles developed by Paul Haast using Farsoon's Flight 403 system. These were designed using 4AM's UltraSim 3D lattice library to achieve perfectly fitted and lightweight insoles for their customers. Using Farsoon's Flight system in tandem with the lattice library, Paul Haast was able to eliminate multiple iteration cycles, which accelerated their design process and enabled them to deliver optimized solutions more swiftly.
Thank you, Ray. So before I finish this and we hand it, I wanted to give the last example of, or the last material that I want to talk is TPU98LT, or which stands for light. The difference between these two, TPU88A Black or natural color is an ester-based material. It's aliphatic and resistant to all the solvents, and it's a high abrasion. It's a material that's significantly used in automotive, the chemistry, but also it can be used for protective gear and all of those applications that I mentioned before. The new formula, which is a harder TPU, it's a ether-based, lower density, has better UV resistance, better water resistance, it has higher rebound and higher rust flex. The materials I mentioned, it is available in different technologies, including Farsoon system. And the example of those is mostly for consumer goods and protective gear, that full part can be printed in one piece that can handle more rugged environment for human application, as I mentioned. So this is the newest one that is available in our portfolio, TPU, different chemistry, but easy to print. And these are the examples of the material. And with that in mind, I just wanted to emphasize more. We have significant data on different materials that we have available on both Farsoon machine and different technology, and we will be happy to provide you. If you're interested in any of them, this is a QR code that you can scan and explore any of them. With that, I just want to hand it back to Alex, and we'll be happy to answer any question.
Awesome. Thank you, Mason and Ray, for the awesome presentation. So at this point, if you have any questions, please drop them in the Q&A session. We'd be happy to answer them both live, or if it's easier to type, then we'll provide links or information in there. So give it a few more minutes. And just a general FYI, this session is being recorded, and we will be releasing this recording shortly after on our social media, so you have access to all the information from the presentation deck. Well, okay. Oh, we have some questions coming in. Yes, we'll be sharing the slides with the participant via recording of this whole session. Okay, we have someone named Annie asked, what kind of batch density percentage can you reach with Farsoon machines? And how does it compare to the other SLS printers? Do either Ray or Johnny wants to take on the question?
I can answer it, and then if Johnny wants to piggyback off of my
Great.
answer with any more information. So we usually try to stay in between 8 to 12% packing density, which is pretty standard for most CO2 systems on the market. With our flight systems, we're able to get a little more. Max still around 15%, and that's just because that since there is less time per layer, we're able to nest parts closer together. All that radiant heat that would usually just kind of sit there and bake off the parts in a CO2 system just because of the longer layer times, uh, doesn't have as big of an effect on our flight system. So we're able to get or nest parts closer together. Obviously, depending on geometry of some parts, you're just not able to pack more dense in a build. But traditionally between 8 to 12 is kind of what you want to stay between.
Yeah, addition to Ray's answers and also for certain kind of geometry, can also increasing to like a 20 to 25 percentage. We already print such kind of things before, without problem. But for certain kind of geometry, with very high in how to say the complex structures and also maybe trap the heat into the parts. In that kind of geometry, we need to consider to reducing a little bit the density or the distance between some of the parts and might help for the final performance. But it's no real limitation that you cannot do that. But most of the time, 8 to 12 percentage is very sufficient.
Great. Thank you, Ray and Johnny. Okay, so we have another question from Dominic. Do your printers offer API to send print jobs to get a real-time updates on remaining print time, printing status, and other details? Can you briefly explain its capabilities?
Yeah, maybe I can answer this question. That's for the machine, and we have our own interface called BuilderStar and MakeStar software, which is generated and developed by Firstone ourselves, and it can tell very good about the printing time with the newest software. Firstone software to our Firstone customer is always upgrading without any fees, so it's a whole lifetime upgrading. And currently, the newest software we can reach is 5% of the accuracy about the printing time and also the remain printing time. And it's really calculate for each layer of the slicing and the calculate its scanning time and also delay time. And finally, we can reach to very good the accuracy of the printing time. We know it's very important to a lot of service bureau to arranging their production schedule. And the pursuit is also keeping moving forward and think about to make like AI technology into the technology finally to make the calculation of the printing time more accurate for the laser technology.
Great. Thank you, Johnny, for that.
Yep.
Okay.
It's a
Any other
very nice
questions?
question. Yeah, it's a very nice question. You know, the laser technology is always very complex, different geometry, different scanning, but we really make it a very good result now, and looking forward to if you want to do more testing on that, and you will find out some nice situation or the nice result on that.
Yes, absolutely. Okay. Any other questions? Okay. So if there's no any questions, we'll go ahead and wrap up the webinar from here, and we'll go ahead and drop off our contact emails into the chat as well, in case everybody wants to get in touch. And with that, thank you for coming, everyone, and thank you for presenting Ray, Mason, and Johnny. And we'll be seeing you shortly. Thank you, everyone.